Hello everyone, this is Hassan from Team 12, and today I will present to you the final presentation of our project, 3D obstacle avoidance for drone using MPCC, the model predictive contouring control. First, I will explain why a drone needs obstacle avoidance tasks. Drone is used in various fields, such as delivery, exploration, and inspection. In such cases, drones may perform missions in complex environments that include obstacles, for example, buildings, trees, and people. Therefore, the ability to avoid obstacles in a 3D environment is essential. This is very essential to avoid accidents that can cause damage to the aircraft or harm to people. However, to the best of our knowledge, there is not been a drone collision avoidance scenario using model predictive control in 3D space. I will review the MPCC, what we are using. So it is a technique for generating optimal control that follow a given path as quickly and accurately as possible. To do this, the problem is defined by minimizing the contouring error, epsilon, which is the error to the path, and maximizing the progress, for example, distance traveled along the path. In practice, the distance to the path and path progress are approximated. This is what we can see in the figure on the right. We approximate because calculating contouring error of path is not trivial. Let me now reiterate our objective once more. Our final goal is to achieve 3D trajectory planning for drones with obstacle avoidance using MPCC. To accomplish this, we have undertaken the following tasks. Firstly, we have formulated the dynamics of the drone, ensuring a clear understanding of its motion characteristics. Secondly, we have created a 3D environment with obstacles and established a reference path utilizing the potential field approach that we learned in the class, which enables effective avoidance of obstacles. Thirdly, we have parameterized the arc length of the paths, ensuring compatibility with the MPCC framework. And fourthly, we have defined a cost function that optimizes the trajectory planning process and successfully implemented the MPCC algorithm within the drone's dynamics. Finally, we have conducted simulations using MATLAB in a 3D environment with obstacles to assess the effectiveness and performance of our approach. I will now proceed with the implementation details. For creating a reference path, we utilized the potential field method, which we learned in the class. To begin, we defined the start position as 0, 0, 0 and the goal position as 10, 10, 10. Additionally, we introduced a spherical obstacle with radius of 1, positioning at 5, 5, 5. It's an example. So to construct the reference path, we assigned the higher attractive force as the drone approached to the goal position. Simultaneously, we introduced a repulsive force to avoid the sphere obstacle, taking into account the size of the drone. The graph on the left shows clearly the resultant potential field, so the goal is attracting, and on the other hand, the obstacle is repulsing. These considerations resulted in the creation of the reference path as shown in the graph on the right side. To utilize MPCC, we needed to resample and parameterize the path using arc length theta. Here's the process we followed. We first sampled the reference points from the potential field method mentioned on the previous page. Next, we resampled the reference points to ensure equal intervals between the points, which is L. And finally, we calculated the P to the D of theta, which represents the parameterized path with arc length theta. For the parameterization, we employed a third-order polynomial path. It satisfies 4 boundary conditions. By solving these for the coefficients A, B, C, and D, we were able to calculate the parameterized path for each interval. It's important to note that this approach differs from the classical methods mentioned earlier. In the classical methods, polynomial trajectories are generated, which include time information. However, in our case, we focused on creating a parameterized path without explicit time information and no trajectory. Now I will explain how we implemented MPCC to a drone. Minimizing true contour error EK to the C is non-trivial, so we used approximated error E hat to the C of theta hat K and E hat to the L of theta hat K. The theta hat K is approximated arc length at K time step. Theta K hat is updated using the following equation in third line of this slide. V theta there is the input I introduced in drone dynamics page. So we can calculate the equations iteratively, then we can calculate approximated contour error and the approximated lag error. Finally, we solve the optimization problem by minimizing the cost function G, the cost function J. Q is here the weight matrix. We set up QC bigger than QL to minimize the contour error more than the lag error. And also we put omega transpose Q omega omega to prevent the drone from fluctuating, which means that body angular rates are changing rapidly. And we added the minus mu v theta of K to maximize the progress of reference position. We simulated our results using MATLAB simulation, and due to the time constraints, we speed up the video by 3 times. As you can see, this video is of avoiding the obstacle, and it is speed up with 3 times. We simulated the results in MATLAB as said before, and here we can see the tracking and position results. The left image shows drone nicely followed reference path. The middle image shows lag and contour error converging to 0 in very few seconds, and in the right image you can see the position error also converges to 0 in few seconds. We conducted multi-obstacles avoidance tasks also. So as we add the obstacles, the agent tries to avoid the obstacles. He tries to avoid them as fast as possible. In conclusion, we utilized MPCC for optimal trajectory planning and applied it in obstacle situations. Simulation results confirmed its effectiveness in handling obstacles. However, incorporating obstacle constraints in MPCC was challenging and led to optimization failures. So to improve the results, utilizing more advanced algorithms for path planning to help in obstacles avoidance is recommended, and that could stay for possible future work. Thank you for your attention.